Our final talk of the session is by Hasib-Al-RASHID. He's a PhD student from University of Maryland, Baltimore. And the topic of the talk is TinyM 2Net, a flexible system algorithm co-designed multimodal learning framework for tiny devices. Hasib, take it away.
Hello, everyone. Good afternoon. I'm Hasib-Al-RASHID, presenting my paper, TinyM 2Net, a flexible system algorithm co-designed multimodal learning framework for tiny devices. Let's look into the brief introduction of mine. I'm doing PhD at University of Maryland, Baltimore County. Dr. Jinosh Mohsinin is my supervisor, and my research interests include multimodal machine learning, deep learning, model compression for edge hardware, and software hardware co-design. So, the motivations of this particular research. Tiny machine learning, tinyML is a field, as we all know, is a field at the intersection of the embedded IoT systems and the machine learning. And we can directly do the data analytics near the sensor by running deep learning models on the very tiny devices powered by the microprocessor and microcontrollers. To mimic the human-like behavior for tinyML systems, tinyML algorithm should integrate multimodal data as well, because all the senses are multimodal. We can see the picture, we can hear the sound. So those multimodal information we are processing, and we get the knowledge from for a particular thing, particular classification, classify a particular thing based on those knowledge. So to mimic this multimodality in the machine learning algorithm, to be specific in the tinyML algorithm, this should be addressed. And but there is a constraint, because tinyML is a very resource constrained hardware. So increased model parameters and computations limit the multimodal learning to be adopted for resource constrained edge and tinyML applications. So in this particular research, we address this challenge and implement multimodal learning on tiny resource constrained hardware. Let's look into the TinyM 2Net. Why we would use TinyM 2Net? So TinyM 2Net is a novel, flexible system algorithm co-designed multimodal learning framework for resource-constrained IoT devices. It can take multimodal inputs such as images, audios, and can be reconfigurable for application-specific requirements. And it can allow the system algorithm to quickly integrate new sensor data that are customized to various types of scenarios. Let's look into the main contribution towards the tinyML implementation that we have made in this research. We have experimented network architecture optimization with depth-wise separable convolutional neural network, DSCNN. And then we compressed our neural network model with mixed precision quantization. After that, our main TinyM 2Net framework was evaluated for 2 different case studies. One of them was COVID-19 detection from multimodal audio, and another one was object detection in a complicated environment where we have used images and audios. And finally, we implemented the TinyM 2Net on community microprocessor, Raspberry Pi 4. Let's revise theoretical background for the depth-wise separable layer. As we all know, since the MobileNet proposed this depth-wise separable layer, it has been very popular for tinyML and edge AI applications. The main difference between a 2D convolution and depth-wise convolution is that 2D convolutions are performed over all or multiple channels, whereas in depth-wise convolution, each channel is kept separate. Depth-wise convolution is one by one convolution across all channels. As you can see, a small example here, if we have input tensor size of 32 cross 32 cross 3 and a filtered shape cross 3 by 3 with 2D convolution, we will have around 35 kilo operation, 35 kilo operation multiplications, but 35,000 kilo multiplications, but in depth separable convolution, the same multiplication actually we reduced by 420 kilo multiplications. So as you can see, the improvement here is 8.4 times. So it's a huge improvement from a vanilla CNN to a depth separable CNN. Next, let's look into the mixed precision quantization. So for mixed precision quantization, what we have done, we have taken the full precision model and then apply uniform quantization with 8-bit and 4-bit. Then we profiled our both uniform quantized 8-bit, 4-bit models in terms of their per layer sensitivity, size, and BOPs, and optimize all the constraints with integer linear programming. So why did we choose integer linear programming to have the mixed precision setting? Because in the literature, you will find a lot of mixed precision mixed precision search space algorithm that were addressing NAS or reinforcement learning, but those algorithms actually very resource hungry and computational intensive. So integer linear programming, on the other hand, is very lightweight. It can give you, based on the objective it will be running on, it can give you the search space optimized result within a second. So that's why we went for ILP optimization. And then we have our mixed precision setting, optimizing all of the constraints. So here, for the per layer, we assume that the perturbation for each layer are independent to each other, and this enables us to pre-calculate the sensitivity of each layer independently. We, here in this work, Hessian-based perturbation is used as the sensitivity metric. And minimizing this sensitivity was our target during the optimization with the ILP algorithm. So next, let's look into the TinyM 2Net framework. TinyM 2Net framework is a framework for multimodal learning on tiny hardware. TinyM 2Net is flexible in terms of number of input, number of layers, hyperparameters based on the application specific requirements. New data modality suited for various settings can be readily included into the device, and some of the input information can be images and other input information can be auditory. So here, as you can see, the input 1, this can be image for as I'll show later. The input 1 for one case study was image, and another one was for auditory signals. And we have used for each unimodal network, we have used one convolution layer and two depth separable layer and one fully connected layer. After that, we concatenated these two modalities unimodal network into by a concatenation layer, and after that, this output of this concatenation layer was followed towards two fully connected layers, and we got the classified labels. So let's look into the case study 1, COVID detection from multimodal audio recordings. So coughing is one of the most common symptom that is reported among patients, and one of the first symptoms for any respiratory illness. In fact, coughing is one of the early symptoms for the most recent infectious disease, COVID-19. Deep learning models for various early symptom detection would be solution, which can be implemented on low power point of care or wearable devices to replace the initial screening by health practitioners to reduce the risk of infection spreading. On the onset of pandemic, we were trying to propose some POC or wearable solution for COVID-19 infected people. So here, for COVID-19 detection case studies, we use a dataset that is from InterSpeech 2021 Compare Challenge. This is actually a part of a larger dataset released by Cambridge, University of Cambridge. In this dataset, there were 929 cough audios from 397 participants and 893 speech audios from 366 participants. Each recording included a COVID-19 test result that was self-reported by the participants. So as the report was self-reported, not the original RT-PCR test report, we termed them as symptomatic COVID positive. So to build a binary classification problem, we got two classes. One is healthy, and another one would be symptomatic COVID positive. So here you can see the details architecture, what we have used for these particular case studies. And with the mixed precision setting, we have got 88.4% binary classification accuracy. As you can see, with the uniform 8-bit quantization, we get 89.6% accuracy, but with uniform 4-bit quantization, we get 83.6% accuracy. So there is a very large gap in the detection accuracy, which we want to overcome with the mixed precision setting, and that we could overcome here with the mixed precision setting. Similarly, let's move into the next case study. Object detection from multimodal images and audios. So researchers in the field of computer vision has always focused on the direction of specific targets in an image. There are still many difficulties in detecting armored vehicle on the battlefield because of the complication of the environment. Researchers previously proposed multimodal learning approach in object detection tasks in terms of multimodal images only. But here in this research, we are targeting in a new task that be multimodal object detection based on the images and audio modality. So in this case study, we have created our own dataset because this kind of dataset is very limited for the battlefield applications. We have created a dataset with 4 different battlefield objects. Those are helicopter, tank, bomb, and gun. And these were the images, and the corresponding audios were collected from 4 different publicly available YouTube videos that are mentioned in the reference. So with this setting and with the network architecture shown here, we have got 96.8% detection accuracy for these 4 classes. And as you can see, there is again accuracy drop from the 8-bit uniform quantization to uniform 4-bit quantization. So we have recovered that accuracy drop with our mixed precision settings. Next, we have implemented this TinyM 2Net on a tiny commodity device, that is the Raspberry Pi 4. We implemented this on so the Raspberry Pi 4 has a Cortex A72 ARM version 8 CPU and 2 GB LPDDR4 memory. Our model loading and visual display of the result was contributing towards the inference time that is mentioned here. And the performance evaluation of TinyM 2Net on the resource-constrained Raspberry Pi 4 was based on 2 metrics, the inference time and the power it required to run the whole inference algorithm. So here in this table, as you can see, the whole TinyM 2Net algorithm was running for the case study 1. The inference time was 1.2 seconds with power consumption of 798 milliwatt. And for the case study 2, the inference time was 1.7 seconds with the power consumption of 959 milliwatts. So as the power consumption still in the milliwatt range, we can claim our TinyM 2Net would be a very good solutions for any kind of multimodal learning approaches running on the resource constrained devices. So next, in the summary, to implement into a tiny hardware, extensive model compression was done in terms of network architecture optimization and mixed precision quantization. To compress, the compressed TinyM 2Net achieves 88.4% accuracy in COVID-19 detection and 96.8% accuracy in battlefield object detection. We tested our TinyM 2Net model on Raspberry Pi 4 to see how they perform when they deployed to a resource constrained tiny devices. Thank you, everyone. So this research was a part of ARL grant. So we thank our investors and our contributors. Thank you, everyone. Any questions are welcome.
Hi. Could you go back to the topology slide, to the architecture slide?
Which slide?
For the architecture slide of the network.
The network
Yeah.
architecture.
We have here as
Yeah,
well.
that's good. So I know there's like a billion things that you can do with this, but one question was, did you ever consider, instead of having two fully connected networks, you could actually concatenate the CNNs before that and then have a single FC layer, and then you could dramatically reduce the number of weights?
Yeah, we could do that, but while we was experimenting, because this network we came up with from the scratch, so all of our results are based on our experiments. So when we actually concatenate the features coming from the CNN layers only, we got a very less accuracy, like compared to what we have reported with the fully connected layers. So that's why we came up with the fully connected layers before concatenating the outputs.
Awesome, thank you. Sorry if I missed that.
Hi, Iqbal Muhammad, Samsung AI Toronto. Very interesting work. I have two questions. The first one is, like, while we're on the architecture slide, you've got the two modalities and then you're concatenating them. In some modalities, the scale of the receptive fields as they're going into the concatenation are vastly different. I'm curious if you experienced that, and if so, you had any solution.
I didn't understand you.
So you've got your fully connected 64s, and then they're getting concatenated at the very ending. So if the two modalities are very different, like audio and video, for example, the scale is going to be very different.
Yeah.
So how do you deal with that?
So this particular network architecture was designed based on this application specific. This was application specific architecture, but as we have claimed in our previous slide as well, this is a very flexible framework. So we can include the number of layers, all the hyperparameters to be tuned to have a better detection accuracy, which would be the whatever the modality of data we are using, but we can tweak the value of the hyperparameters to have the better accuracy.
Okay, the second question is, in case study 1 with the COVID cough thing, what was the multimodality of it? I didn't understand what the two inputs were. One of them is audio, what's the other?
So here the multimodality is in terms of multimodal audio. So one audio was cough sound, another audio was speech sound. So two different types of audio we are processing simultaneously to get the COVID detection results. So that's how we turned it as multimodal audio.
For the same person, so it's
for the same person,
not coughing.
Yeah, all the
coughing.
cough and speech was coming from the same particular person.
I see. All right, thank you.
Thank you.
Hello, I'm Sapna from UCLA. So I was wondering, I don't see any benchmarks. Like there are, other multimodal, frameworks as well. So maybe did you compare against them and show, in terms of model size, accuracy, like how does it compare?
So very good question. As of now, while we are searching for the related works, we found very limited number of literatures which was targeting multimodal implementation in the tinyML devices. So there would be some multimodal sensor integrating into the tinyML devices, but in terms of images or audio, there's very limited work, and that's why we are claiming during the first slide, as you can see as well, we are claiming this was we are targeting to solve this particular problem, to integrate multimodal images and audios into the tinyML devices.
Okay,
So
my
that's how we couldn't show any.
Next question is, I'm aware that
benchmark.
such things exist for like Jetson Nanos and our Raspberry Pi. So second question is, do you think Raspberry Pi is a tinyML device, or is it kind of like an edge device?
Yeah, so to be honest, the tinyML device, as we can see here, our implementation power that we are getting from the algorithm, we are getting in the milliwatt range. So even if we are implementing on a Raspberry Pi, although it has a very limited number of resources, but if you can consider it as an edge device, it can be, but the power profiling what we have done on Raspberry Pi, it is showing that even if you implement this on a microcontroller-based tinyML devices, it can be still a tinyML algorithm. TinyM 2Net would be a tinyML algorithm. So that's what we have done profiling on Raspberry Pi.
Okay, thank you.
Thank you.
All right, with that, we'll thank our speaker again.
And we are very thankful for our sponsors. The premier sponsor this year is Edge and Pulse. And then executive sponsors are ARM, DeepLight, Qualcomm, and Syntiant. Platinum sponsor Analog Devices, BrainChip, Infineon, Clickertech, Latent AI, NXP, Reality AI, Renaissance, Sony Semiconductor, and Synaptics. Really very diverse company, great companies who are really driving tinyML forward. And gold sponsors for the Hub, Micro AI, Prophecy, Seed Studio, SenseML, ST Microelectronics, SynSense, XMOS. And we have a list of civil sponsors: Avion Devices, Aspinity, Seva, EMSA, Greenwave Technologies, Grovity, Hymix, HOTG, Imagimob, ITMIS, Lattice, Nota, OmniML, PixArt, Plumerai, Kixo, Rachner, Rixen, SAP, StreamAnalyze, Texil, and Google. So we are very thankful for their support, and more importantly, for them being part of this community and driving it forward.